Okay, your Quest 3 corrections are due today. If you need like a couple more hours, I will take them a little later today if you need it, but that's the very latest, okay? Yeah, put them in your folder when you're ready, and if you need to hand them in a little bit later, you can bring them to my office. It's just down that hall, 419, North 419. Okay, so today we're going to cover lessons 25 and the beginning of 26. This material that we talk about today will not be on Quest 4 explicitly, but some of it, a lot of the tools we're going to use in today's lesson are going to be on the Quest, right? So the new stuff from today is not, but we're going to be solving quadratic equations today. We're going to be graphing parabolas today. So we're going to be looking at word problems. Word problems themselves will not be on the test, but the tools we use when we start solving them will be on the test. Okay, so today's some new stuff, but also some good practice for what's on the Quest 4. Quest 4 is going to cover lessons 19 through 24, so it starts with factoring and goes up through the quadratic formula. So we got factoring, solving quadratic equations, graphing parabolas, and the quadratic formula. So for the Quest, you have your usual tools to prepare. You've got your practice problems with solutions in Moodle. You have homework, old homeworks that you can go and click try similar problem and get a bunch of new problems if you want. For the Quest itself, you can bring one sheet of notes with you, anything you want written on it. Yes. Yeah. Yes. Yes, there is a section of the test which it's like a page of the test where I give you several quadratic equations to solve. And I said, solve these quadratic equations using any method other than the quadratic formula. The box method or square rooting both sides. The discriminant doesn't help you find the solution. It only helps, it tells you what kind of solution there is. And then if you were to go from there, you'd probably use the quadratic formula. Yeah. So yeah, not the discriminant. You would be doing the box method, which is another word for factoring, or you taking the square root of both sides. Yep. 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 Either of those two, just not the quadratic formula. Yep. Sure. Yeah. Whatever works, you can use. Yep. Just not the quadratic formula. So things you're allowed to use on Quest 4 are one page of notes, a scientific calculator, and I will bring a few extras if you need to borrow one, and you can use your Perfect Powers sheet if you've grown to rely on it. You're welcome to use that. Right, like I said, one page of the test has several quadratic equations to solve. Solve them with any method other than the quadratic formula. And then there's a separate question on the test where you're supposed to use the quadratic formula. Yes, yeah. Okay, so let's start looking at today's lesson, lesson 25. So we're going to tackle some story opportunities, a little positive spin on the traditional word problems. Okay. And they're going to lead to quadratic equations, right? So there will be no word problems on your Quest 4, but we'll get some practice today solving quadratic equations. All right, so we have a box with a square base and no top. Okay, so look at the picture on the right. The base is a square, there's no top with the box. And we're going to create this thing from a piece of cardboard, a square piece of cardboard, by cutting squares out of the corners and folding up the edges. Okay, so here's my piece of cardboard. If I rip squares out of the edges, out of the corners, squares out of the corners, this is not the most precise thing to do, way to do it, but I ripped a square out of every edge, so it looks like a weird looking cross kind of thing, right? And then you can take the flaps that remain and fold them. Fold them up 90 degrees, and you've created a box, right? Okay, so everybody can sort of picture how this thing is being made. We're starting with a square, and we're going to cut the squares out of the corners are going to be 4 inches on each side. All right, so I'm trying to create a box that will hold 100 cubic inches. What kind of measurement is cubic inches? Is it a length? Is it an area? Is it a volume? It's a volume. Yeah, cubic inches is a volume. Okay. So the question is, what should be the dimensions of the square piece of cardboard? How big of a square piece of cardboard do I need so that if I cut out 4-inch squares from the corners, I get a box with volume 100 cubic inches? So my first step is to introduce a variable, and I'm going to let the variable be the thing they asked me for, right? What should the dimensions be, right? So that is, how big a square do I need? So I'm going to let that be b. B is going to be the length of a side of the square. So this is b, the whole side. And it's a square, so every side has that length. So that's the side before we cut it, right? Before we cut out any squares, it has length b. And I want the box to hold 100 cubic inches, so that means the volume of the box is 100. So I need a formula for the volume of a box. So volume of a box is length times width times height. Length, width, height of the box. Sound familiar? Okay, so I'll just leave that. Now, since B, called it B, B is the length of a side of the square before it's cut. The length of the box after we cut out 2 4-inch squares. Right, so my length of the box is this. This is the base of my box because the other flaps are going to get folded up. What is this length right here in terms of B? B minus 8, yeah, because this whole length was B, and then I have to take away 4 for what I'm cutting here, 4 for what I'm cutting here. So my length is actually B minus 8. And then because it's a square, so is my width. Over here, this is also B minus 8 because the base of my box is a square. So W is also B minus 8. Okay, and then looking at the diagram, the height of this box is 4 inches. H is 4. Okay. So I'm going to rewrite volume equals length times width times height. I'm going to replace length with B minus 8. Replace width with B minus 8. And replace H with a 4. And then we're given that the volume of the box is supposed to be 100 cubic inches. So in this equation here, I substitute for V. I replace the V with a 100. So I have 100 is B minus 8 times B minus 8 times 4. All right, sort of the most efficient first step here would be to divide both sides by 4. But if you don't see that, we're gonna just solve it without doing that, so you can see that we get the same answer. So I'm just going to multiply everything out on the right-hand side. So I have to multiply B minus 8 times B minus 8. So I have 100 equals. You can either draw a box or use foil or the lobster claw, however you learned to multiply those things. I think I'll do a quick box over here. B minus 8, B minus 8. B times B is B squared. And I get negative 8B, negative 8B, and positive 64. Combine your like terms of the negative 8B's, and I get B squared minus 16b plus 64, and I still have the times 4. Distribute the 4, right? So I have 100 equals 4b squared minus 64b plus 256. So it's a fairly routine looking quadratic equation now. This is the kind of thing we've been solving for a couple of days, right? Quadratic equation. So whenever you have a quadratic equation, typically your goal is to get one side to be 0, your first goal. So then you can either factor or use the quadratic formula. So I'm going to have to subtract 100 from both sides so that I have 0 equals 4b squared minus 64b plus 156. Right. Before I start trying to factor or use the quadratic formula, is there a GCF? 4, 64, and 156. Is there any number that goes into all of those? 4. Yeah. And if you're not sure, you can just grab a calculator. 4 definitely goes into 4. You could do 64. Does 4 go into that? Yep, 16 times. And 156 divided by 4, 39 times. Okay, so I'm going to factor out a 4. So I get 0 equals 4 times b squared minus 16b plus 39. It's 39, right? Yep. Okay, so I'm just going to copy what I had on the previous page here. 4 times b squared minus 16b plus 39. Okay, had I divided both sides by 4 back in part G, we would have had an easier time getting the final equation in part H, but we got there, right? So it doesn't really matter. And the next step is to factor and use the zero product property. So I have 0 equals 4 times, and I would like to factor b squared minus 16b plus 39. So you can make yourself a box, or you can do trial and error in your head, whichever way you'd like to do it. I'll make a box. I just need a little more room. Right here. Okay, so we always put the first term in the upper left, b squared, and the constant term in the lower right, and then you multiply them. B squared times 39 is 39b squared. All right, so I want to come up with factors, things I can multiply together to make 39b squared. They have to either both be positive or both be negative to make them multiply to a positive number. And they want them to add together to be a negative number, which means they have to both be negative. Good. All right, so I could have -1 and -39. Do they add to -16? No. Okay, what else goes into 39? 3 and 13, yeah. So I could have -3b and -13b. Those do add up to -16b. So that's what goes in your other two boxes, -3b, -13b. Then you look at the first row and you pull out the GCF. B squared and -3b, what do they have in common? B, yeah. So I pull out a b. Okay, then I do b times what is b squared? B. B times what is -3b? -3. And b times what is -13b? -13. Okay. So we've got it factored. B minus 3 and b minus 13. All right, so multiplying three things together here, right? 4, b minus 3, and b minus 13. I've got three factors, and the answer is 0. The only way you can have a multiplication problem whose answer is 0 is if one or more of your factors is 0. Right? At least one of your factors has to be 0. So in this case, either 4 is 0 or b minus 3 is 0 or b minus 13 is 0. 4 equals 0. Does that have any solutions? No, so this just ignore, right? No solutions here. B minus 3 equals 0. That's true if b equals 3. Okay, and b minus 13 equals 0. That's true if b equals 13. So b equals 13 or b equals 3 look like solutions. We should check our solutions, though, against the reality of the problem. Remember, this was a physical box we're building. We should double check that it's actually going to work, right? So if we choose b equals 13, the original square has length 13 inches. It's helpful to go back and remember what b was representing. It's the length of the whole square before you cut it. So if b is 13, then you take away 4 inches for one square and 4 inches for the other little square. You're left with 5 inches, right? Okay, so that means that our box, when I build it, will be 5 by 5 by 4, or 100 cubic inches. So that's good, legitimate solution. But if the original square has length 3, which was our other solution, if this length is 3, I can't cut away 4 and 4, right? There isn't enough square. So if I do 3 minus 8, I get a length of -5. You can't have a length in real life that's a negative. It doesn't mean anything. Okay, so if the original square has length 3 inches, subtracting 2 fours gives -5 for the length and the width of the box, but that's impossible. Okay. So b equals 3 does not give a meaningful solution to the problem. However, it does actually solve the equation, right? -5 times -5 times 4 is 100. But because -5, you can't build something that has length -5, we eliminate it, and the only solution is b equals 13. It's the only way to build this box that has 100 cubic inches of volume. All right, what do you think? Any questions? I know. Each problem's a little different, and you have to like spend some time thinking about it. The most important thing is to define your variable. I'm going to let you try some. Everybody's attention back up at the front here. We're going to move on. I'm going to do the lesson 26 activity demo. If you're done with the 25 activities after this demo, you can start the activities for lesson 26. If you're not done, just go back to where you left off in the class 25 activities. Okay, so we're going to talk a little bit more about graphing parabolas for this lesson. Okay? And we're going to use what we know about graphing parabolas to use graphs to help us answer some questions about story opportunities / word problems. Okay, so here's a graph, graph A. We've used this particular graph in several previous lessons. It's the graph of y equals x squared plus 5x minus 6. And I want to figure out the x coordinates, the coordinates of the x-intercepts. So we've got 2 of them. That first one looks like it's at -6, 0. And the other one is at 1, 0. All right, so I want to find the x coordinate of the vertex by what? How do you find the x coordinate of the vertex? Averaging the answers we got in part A. Okay, so I add -6 and 1 and I get -5. -6 plus 1 and I divide by 2. That's how you average. Add them together and divide by 2. And remember, we use x with a little sub v to mean the x coordinate of the vertex. So this comes out to -5/2 or -2.5. So it turns out there's another way of finding the x-coordinate of the vertex for a parabola. Also very easy. If your equation looks like ax squared plus bx plus c, the x-coordinate of the vertex can be found by using the formula -b/2a. Does that sound familiar? It's like a piece of the quadratic formula, right? -b/2a. So that's where it comes from. I'm not going to derive it for you to show you why it is that, but it comes from the quadratic formula. In general, to find the y-coordinate of the vertex, just take the x-coordinate of the vertex and sub it into your original quadratic equation. So let's look at how we could use our new fancy and simple formula to find the vertex of x squared plus 5x minus 6. So in this case, a is 1, b is 5, c is -6. So I use -b/2a. I replace the b with a 5 and the a with a 1, and I get -5/2 or -2.5. Right? So exact same answer you get when you average the x-intercepts. And then to find the y-coordinate of the vertex, denoted y sub v to mean y-coordinate of the vertex, take the x value we just found, the -2.5, plug it into your original quadratic equation. So my original quadratic is x squared plus 5x minus 6. I just found the x-coordinate of the vertex, so plug that in for all the x's. So -2.5 squared plus 5 times -2.5 minus 6, and then you can do that all out in your calculator and you get -12.25. So the coordinates of the vertex are going to be -2.5, comma, -12.25. All right, that vertex that I just found, -2.5, -12.25, is right here. Vertex. Okay. Is that point on the graph a maximum point or a minimum point for that graph? Minimum. It is the lowest point on that graph, so it's a minimum. Because the parabola opens up. Yeah. Yes, because the a value is positive. Good. Yeah. So this parabola opens upward because a is 1, which is positive. So that means the vertex is a minimum. It's the lowest point. It's often useful to be able to determine the smallest and largest value a quantity can take on. So for example, companies try to minimize costs and maximize profits. It's helpful to know what the lowest value your costs can be, what is the highest value your profits can be. So if you see the word maximum or minimum, or biggest or smallest, or highest or lowest, or any synonym of those words, right? In a word problem that you're solving, there's a very good chance that the answer is found by finding the vertex of the parabola, right? You want to find the highest or lowest point on the graph. So we began graphing parabolas a couple of classes ago, and now that we have an easy way to find the vertex, and not to mention one that works to find the vertex even if there are no x-intercepts. We never did any problems like that because I very carefully curated the problems that I asked you to do. Now we can graph certain kinds of parabolas that we couldn't before, and we have a slightly revised 6-step process. Okay? So before we had a 6-step process that involved finding the vertex by averaging your x-intercepts. I'm going to replace that with finding the x-coordinate of your vertex using our new fancy formula, -b/2a. So I'm not going to read it all to you. We're just going to do one together. Okay, so step 1, I want to know, does this thing open up or down? Down. How do you know that? -3x squared. The coefficient on the x squared, the number touching the x squared, is negative. And for some people, it's very helpful to rewrite this in descending powers of x. So you have x squared, then x, then no x's. And then it's clear that a is negative, which means this parabola opens down. All right, next thing I want to figure out is the y-intercept. So that's step 1. Step 2, y-intercept. In general, you find y-intercepts by making what 0? X. You make x 0. And then you figure out what y is. So y equals -3 times 0 squared plus 2 times 0 plus 4. And that comes out to 4. So my y-intercept is actually the point 0, 4. Because I made all my x's 0, my y turned out to be 4. So 0, 4, I can plot that point. Okay. Step 3, x-intercepts. So to find x-intercepts, make y 0. So I've got 0 is -3x squared plus 2x plus 4. I could try all day to factor that, but it turns out that you can't do it, right? So what do you do if factoring fails? The box is factoring. The quadratic formula, yeah, quadratic formula. So x is -b plus or minus the square root of b squared minus 4ac all over 2a. So I'm going to replace b with 2, a with -3, c with 4. So this is going to become -2 plus or minus the square root of b squared minus 4 times a times c all over 2 times a. Okay, I'm going to try to simplify what's under this square root. 2 squared is 4. -4 times -3 times +4. The negative times a negative times a positive, that's going to make a positive. And 4 times 3 is 12, times 4 is 48, all over -6. So this is -2 plus or minus the square root of 52 all over -6. All right. If you noticed in the directions, they said round your x-intercepts to the nearest hundredth. So I'm just going to use my calculator to figure this out. So this is actually 2 separate x-intercepts, -2 plus square root 52 over -6, or -2 minus square root 52 over -6. I'm going to borrow your calculator for a second. Okay, so -2 plus the square root of 52 divided by -6, and I get -0.87. They said round to the hundredth. -0.87. And I should use squiggly equal signs here to mean approximately equal to instead of a regular equal sign. And then -2 minus root 52 divided by -6 is 1.54. Thank you. So there are my x-intercepts. So I try to put them on my graph. -0.87, that's almost -1. And 1.54, about halfway between 1 and 2 x-intercepts. Okay, step 4 is going to be to find the location of my vertex. We could find it by averaging these two, right? I'm going to use our new method, the -b over 2a method. So vertex. So the x coordinate of my vertex is -b over 2a. So that's going to be -2 over 2 times -3. So that's 1/3. And then the y-coordinate of my vertex, I get by taking my 1/3 and plugging into my original formula. Okay, so that my original formula is -3x² plus 2x plus 4. Okay, so this is -3 times 1/3 squared plus 2 times 1/3 plus 4. Type this all into a calculator. I get 4 1/3. Four and 1/3. So now I know my vertex is at 1/3, comma 4 1/3. And I can plot that point. 1/3. So 1/3 of the way between 0 and 1, comma 4 and 1/3 is like right there. And that is also your axis of symmetry. There's one more point I can get. The point that is symmetric to the y-intercept on the other side of the axis of symmetry. So it would be 2/3, right? Because the 0.04 is 1/3 away from the axis, because this is x equals 1/3, right? So you have to go 1/3 on the other side, which would land you at 2/3. 1/3 plus 1/3 is 2/3. So this is really hard to draw this all in here. So your then you can connect the rest with a smooth curve. So this point right here that I just added, that is at 2/3, comma 4. All right. So that's our new method for graphing parabolas. It's almost the same as before, just have a slightly new way of finding the vertex. Okay, so wherever you were working before, you can pick up there. You can just go back to where you were. If you were finished, you can start the activities on page 204. Okay. And we'll pick up with these activities the day after our quest.